Hello everyone, this is Vatsala Chaubey. Today I am going to talk about Digital Signal Processing Lab 4. In this particular lab, we dealt with the discrete Fourier transform. So, let's just dive straight into it. What is a DFT? Discrete Fourier transform is a transform which enables us to evaluate the frequency domain parameters of a signal, like which component frequencies are present in the time domain signal. And apart from this, we can also know which frequency component has the higher magnitude, how the phase get affected when the frequency of the signal changes. All these things can be known using the DFT. So how is the DFT actually detected? DFT is defined as x of k equal to summation n equals 0 n minus 1 x of n dot e ki power minus j 2 pi by n by into nk. So once we get the DFT values, how we can use them for our analysis. In this particular lab, we'll be using our previous PPG signal and try to estimate the pulse frequency using a DFT. So the procedure, the PPG signal is smoothed out using a moving average filter. This we already know, the moving average filter, how it is done. This is done to remove the high frequency noise in the signal. Then the endpoint of DFT of the signal is calculated using the above equation. We have used this equation to calculate the endpoint DFT. Now, once we get the endpoint DFT, we will try to find the point where the DFT, the frequency component's magnitude, is maximum. So why do we want to do this? We want to do this because the component which has the highest frequency is the component which is the most dominant. So in a PPG signal, the most dominant component should be the frequency component related to the pulses or the heartbeats. So once we get the value of k, or the index value for which the magnitude of DFT is maximum, we can get the corresponding frequency using this formula. Frequency is equal to k times frequency by the number of samples. Once we know the highest frequency component, we can find the pulse rate to be 60 times the frequency calculated above. Now coming to the code. As always, all the codes can be found in the repository. Float. Here we have taken a PPG signal containing 75 samples, and this WR, WI, these are the DFT matrix weights. These are the real weights, WR, and these are the imaginary weights, WI. As you will notice, this is an equation involving e ki power j terms, that is cos theta plus I sin theta. So in Arduino, we cannot handle them both together. So I have split the real part separately and the imaginary part separately. Now coming to the main equation. In xt, here we have taken the moving average filter of our input with size 2, see the moving averaged output, and here we are taking it. Now coming to the real and imaginary part. XFI, the frequency component real value, in XFI the frequency component's imaginary value in magnitude for the all 75 components. WRIJ, that is weight at ith position and jth position, where I denotes the n, small n in the above equation, and j denotes the small k, is equal to cos of 2 pi n by small n into small k divided by capital N. As you can see here, n is capital N is 75, small n is j, and capital N, small k is I. So this way we calculate the weights of the real components, weights of the imaginary component, and then the real component of I term will be summation of the real components across j. xt is equal to x of j into real weights summed over all the j components. Similarly, the imaginary will be xfi of I is equal to xt of j into weights of imaginary summed across j. And finally, we calculate the magnitude as square of real plus square of imaginary with square root of the entire thing. Once we get this, we assume the peak to be at 0 and find the peak location, maximum peak location. The maximum value is assumed to be 0. If maximum value is less than the magnitude of k, then we update our maxima and store its location. Once we do it, we'll get the maximum value of the signal. maximum value, the index at which the maximum frequency component takes place. Now this is the pulse speed, peak into 20. How does this 20 go? Okay, now we know fs here is 25, the number of samples were 75, so this will lead to 1 by 3, and we know that to get the pulse period we need to multiply this entire thing by 60. So 1 by 3 into 60 will give us 20 into k. The same thing we have done here. We found out the peak value, that is k, from here and multiplied it with 20. Now coming to our baseline methods: autocorrelation of PPG signal, frequency estimation, pulse rate estimation using PPG. This we have already done in the previous lab, as you remember, so I'll just skim through the code. Here we have taken the moving average, subtracted the mean, and did some block processing. Last time we had 4 blocks. Since the number of samples were huge, here we have only 75 samples, so we are taking only 1 block and trying to find the pulse period. Now we find the autocorrelation of the signal. Again we find the first maxima after the 0th position. This entire things find the first maxima after the 0th position or the first 0 crossing. Similarly, at last time, divide the position by the sampling frequency, which is 25 here, and divide the whole thing by 60 to get the pulse period. Now coming back to the results, this is our original PPG signal. This is the DFT of the PPG signal. Once we filter it using moving average, this is what the DFT components look like. Essentially, here we also wrote a MATLAB script just for verification purposes to see and compare within both the methods. So now the magnitude response of the DFT as plotted in MATLAB along with the autocorrelation. This is what we got: the DFT in MATLAB and the autocorrelation in MATLAB. As you can see, these two things are quite similar. This plot is similar to what we saw last time. Now coming to the result values. So DFT on Android gave us a pulse period of 60 beats per minute. DFT on MATLAB gave us 80 beats per minute, and autocorrelation on Arduino gave us 71.43 beats per minute, whereas autocorrelation on MATLAB gave us 68.18 beats per minute. Coming to the error calculation, assuming the results obtained through autocorrelation MATLAB to be the correct values, the errors and other methods are as follows: DFT on Arduino is 12%, almost 12%. On MATLAB is almost 13%, and autocorrelation Arduino is 4.7%. So as we can see, the actual value the error on the autocorrelation functions are small as compared to DFT function. This is due to the one of the reasons of this is the sampling frequency. As you can see here, this term is multiplied by 20, like the index value where the maximum DFT occurs is multiplied by 20. So this can only be multiples of 20, like 20, 40, 60, 80. You cannot get values between 20 and 80, 25. So this is due to the sampling frequency which we have. If we have a different sampling frequency with more number of samples, we could have gotten a better resolution. Maybe we could have gotten values between 60 to 70, 70 to 80, 70, 70, something like that. The major constraint is due to the sampling frequency, and that is valid because DFT is a frequency domain transform. So the way we sample the signal sure to introduce changes to the frequency component. Coming back to the final conclusions of this experiment. To this experiment, we used a DFT and understood how it can be used to get frequency domain parameter, and how it is limited in a sense as to how we sample our signal. If the sampling is not done correctly, we will have difficulty in using the DFT. Okay, thank you.